Hello all, welcome to Advanced Engineering Physics, Magnetic and Dielectric Materials, Part 7. This is Dr. S. Deepthi, Assistant Professor in Physics, Department of H&S, MLR Institute of Technology. Now, in this video lecture, we are going to have ferroelectric and piezoelectric materials, okay, and also some applications. Well, let us see some applications also, okay. So, ferroelectric materials. What are ferroelectric materials? What are ferromagnetic materials? Yes, the ferroelectric materials have similarities between them with the ferromagnetic materials. So, ferroelectricity, substances exhibiting electronic polarization even in the absence of external field are called as ferroelectric materials. Okay, so whenever the idea comes here, electronic polarization means this occurs in all materials where there will be net shift in the charges of both positive and negative charges. Okay, this is what we are going to remember in the electronic polarization. So here the substances exhibiting electronic polarization even in the absence of applied electric field. This phenomena is called as ferroelectricity. Example: Rochelle salt, lead titanate, okay, lead zacronate, titanate, lead zacronate titanate, lead zacronate, okay, lead lanthanum zacronate titanate. These are the examples. Properties: have peculiarly large dielectric constant. They exhibit hysteresis like ferromagnetic materials. That's what we have already discussed. We have already discussed that about ferromagnetic materials, and this is ferroelectric materials. They are also having the hysteresis curve or loop. Okay, so see here the ferroelectric materials. In the polymers comes under this, and inorganic also come under this. Metal organic framework and organic inorganic perovskites also completely comes under ferroelectric materials. Okay, so these are the properties of ferroelectric materials. Have peculiarly large dielectric constant. They exhibit hysteresis phenomena like ferromagnetic materials. So the lagging of it is occurs between P and E, polarization and electric field. The polarization is not zero even when the external field is zero. Ferroelectrics follow Curie-Weiss law. Okay, psi is equals to C by T minus theta. Here C is the Curie temperature, theta is the transition temperature above which ferroelectric substances become paraelectric substances. Spontaneous polarization becomes zero at transition temperature. All the ferroelectric materials are pyroelectric, however, the converse is not true. Okay, they exhibit the phenomena of double refraction. Now, piezoelectric materials. When certain crystals are subjected to stress, the electric charges appear on the surface with a certain distance of separation. This is called as piezoelectric effect. So, subjected to stress means it is mechanical stress. Okay, mechanical stress means let us consider a block is there. Okay, block of material is there. When these particular materials are subjected to stress means when we just apply some pressure by using hammer like substances, then these particular materials are going to develop some amount of electric field. Electric charges appear on the surface. Okay, so the electric field will be created on the surface of the particular material. This is called as piezoelectric effect. Okay, there is a converse of piezoelectric effect is there. Whenever in such materials, whenever we are going to apply the electric field, then a stress will be observed in the particular material. That is called converse piezoelectric effect. Okay, so the crystals exhibiting piezoelectric effect are called as piezoelectric crystals, and this phenomena is called as piezoelectricity. Examples: quartz, Rochelle salt. Rochelle salt is also example of ferroelectric materials. Tourmaline and other piezoelectric substances. Piezoelectric strains are small and corresponding to the electric field. Electric fields are large. So, non-centrosymmetric crystals are exhibiting this property. Okay. So, see here in a piezoelectric material, Environmental monitoring will be there. Wearable electronics will be developed using physioelectric electronics, and energy harvesting will be there. Biomaterials are also having uses these physioelectric materials, and structural health monitoring can also be done by using physioelectric materials. Physioelectric materials. This is the structure of a physioelectric material. We have seen the structure of physioelectric material. So, the three-dimensional lattice of quasi lattice. Before the constant is applied, the dipole moment at each lattice point is 0. Okay. When the pressure is applied, first of all, the dipole moment is 0 before the application of mechanical stress. Okay, when the pressure is applied along x-axis, the angle increases, gives rise to the polarization along y-axis. Okay, in the structure, the center of symmetry, the opposite ends are identical in any direction, so constraints do not produce any polarization. Okay, this is about physioelectric materials. Now, we are going to have the applications of dielectric materials. So, till now we have learnt about ferroelectric materials, piezoelectric materials, and these are the materials where they have their own properties of the materials. Now, we are going to have the applications. In that applications, we are going to read about ferroelectric random access memory, ferroelectric random access memory, afterwards load cells, and also fire sensors. Okay, these are the three we are going to learn about in this video lecture. Now, what is ferroelectric random access memory, FERAM? You might have learned about this thing, FERAM, frequently. FERAM is the ferroelectric material with non-volatile memory storage. Okay, so how this FERAM is going to be fabricated? The material used for the fabrication of a ferroelectric material or ferroelectric FERAM are lead zirconate titanate and strontium bismuth tantalate. Okay, strontium bismuth tantalate and lead zirconate titanate. These are the most common materials. What is the structure of FERM? So, here in this structure we are using NPN transistor, and also a bit ferroelectric material is kept over here. A word line will be there, bit line will be there. Okay, so this consists of typical RAM is a memory cell. Okay, remember FERAM is a memory cell. So, it consists of a bit line, word line, transistor and ferroelectric capacitor. The ferroelectric layer inside the capacitor stores the information by switching the polarization direction. So, what is the ferroelectric material's importance over here? It stores the information by switching the direction of polarization. Okay, so that is, it is kept in between the capacitor, plates of parallel plate capacitor. So, first before starting of the dielectric materials, in the introduction of dielectric materials, we have already come across the one thing, that the dielectric materials are used as a charge storage, okay, charge storage capacitor, storage things. Okay, so here the application we are seeing. So, what they have done here in this small structure, they have inserted ferroelectric material between the plates of this is a parallel plate capacitor, and between the plates of parallel plate capacitor they have inserted the ferroelectric material. Okay, so next, working principle. The FERAM cell contains a ferroelectric capacitor and a transistor. The ferroelectric material can switch the polarization between the two stable states when electric field is applied. So, these two polarization states represents the binary data: 0 polarization in one direction, 1 in polarization in opposite direction. Stored polarization remains even if the power is turned off. This is called as non-volatile memory. Okay, so now read operation. A small voltage is applied to the ferroelectric capacitor. Depending upon the stored bit, the polarization may remain the same or switch the direction. This change produces a detachable electric response, allowing the circuit to read whether 0 or 1. Okay. Now right operation. A specific voltage is applied to force the ferroelectric capacitor into desired polarization state. The polarization direction determines the storage data, 0 one direction and 1 in opposite direction. The polarization remains stable after removing the voltage. Right operation completed. Okay, so we do have two options over here. One is read option, another one is write option. So for read option and write option, we are going to switch between the zeros and ones. The bits will be switched in between them. Okay. Now key advantages of FERAM. It is non-volatile, retains data even with without the power. Fast read and write speed compared to the flash and EEPROM. Okay. So next, lower power consumption, higher endurance. Okay, can be written many times without degradation. This is about ferroelectric RAM or FERAM. Now coming to load cells. So load cells are operated by converting mechanical deformation into electrical output. So this works under the principle of piezoelectricity. So the mechanical work is converted into electrical work, means it is a piezoelectric material. When a force is applied, the internal structure of the load cell deforms slightly. This deformation causes the electrical properties of the sensing element. Okay, so the load cells are prepared by using these many materials. So the typical materials: polydimethyl isoxane, polyurethane and styrene, butadiene styrene, polyvinyl fluoride and acrylate based dielectric polymers. These are the materials that are used over here. Any material can be used in preparing the load cells. So working. So what is the working of the load cell? Force input. The load cell is designed to detect the forces such as tension, compression, shear, pressure or torque. Deformation. When the force is applied. So when the force is applied on the load cell, simply this is the for example, this is the let us consider this is the load cell. Then when the force is applied on the load cell, mechanical force is applied on the load cell, then what happens? The internal structure will be slightly deformed. Now the sensor response. The strain gauge or capacitive sensor responds to the deformation by changing the electrical resistance or capacitance. So a sort of sensor will be kept over the particular material, and that sensor notes the deformation, small deformation changes in the particular material. Okay. So the electrical output. The change in the electrical property is converted to a proportional electrical signal. The signal represents the magnitude of the applied force. So the electric signal itself represents the applied magnitude of applied force. Measurement and calibration. The output signal is processed, calibrated and displayed so that it accurately reflects the applied force. Okay. This is about load cell. And what are the advantages of load cell? It has high accuracy, wide measurement range, high reliability and easy integration with the digital systems and lower consumption. These are the advantages of load cells. Okay. Now coming to fire sensor. So these days sensors are mostly used for each and every purpose. So we are frequently using the sensors. Whenever we go to a shopping mall, then there the doors will be closed and the doors will be open whenever we enter, some person enters. Like that, at each and every places we are seeing about the sensors. The sensors sense the movement of the particular person or movement of something. So here one sensor is there, which is fire sensor. Is a device used to detect and respond the presence of fire. So to prevent the fire accidents or to prevent the much loss in the fire accidents, this sensor is used. Okay. It works by sensing infrared radiation emitted by flames or monitoring changes in the dielectric properties of the materials exposed to heat. Fire sensors rely on changes of dielectric constant of the material when exposed to heat. So the materials are used here in order to fabricate the fire sensors: xenon gas, dielectric coatings such as glass, quartz or ceramic. Polymeric dielectric materials are used to insulate the electrodes. Okay. So the working of fire sensor, infrared radiation detection. Flames emit the infrared radiation over the specific wavelength. Sensor detects this IR signature. Sensor activation. The flame sensor uses photodiodes or other IR sensitive components to detect the radiation. When IR is detected, the sensor becomes active. Signal processing. Once IR is sensed, the device generates an electric signal. This signal is sent to control the circuit for analysis. Alarm triggering. So the control circuit compares the signal and the with a present threshold. If it indicates the flame, the system triggers the alarm and activates the safety mechanisms. So whenever the fire is kept near the materials, this sensors, then the fire sensor activates and the alarm buzzes. Due to that, we are going to see how the total thing takes place. Okay, so activate and the safety mechanisms are also activated in the fire sensor. So advantages of fire sensor: it has fast response, it has high sensitivity, reliable operation and lower power consumption and wide application. It uses in homes, industries, laboratories and safety systems to prevent fire hazards. Okay, this is a fire sensor, and with this we have completed our dielectric materials, and also we have completed the magnetic and dielectric materials total unit. Okay, thank you.